Alright, so we're going to go over the answers to this insurance assignment. So, what's the difference between a statement and a sentence? A statement's always true or always false, but it's never both. For example, for all real numbers A, B, and C, if A times C is equal to B times C, then A is equal to B. This is always true. Yeah. A sentence can be either true or false. So here's an example of a sentence. 4x is an integer. Sure, if x equals 1, then this statement is true. But if x is equal to 1/5, then this sentence is false. So here's an example of something that is both true and false, depending on what x is. So how do you find a counterexample to a statement? You can only find counterexamples to universal statements. So find one instance for which the statement is false. So, for example, all students will study for this test. A counterexample would be I find one student who did not study for the test. That would prove that that would prove that the statement was false. The negations for universal statements and existential statements. So a universal statement looks like this: for all x in S, P of x. So everything in S has this property. Its negation would be there is one x in the sample space such that it didn't hold that property. So it's kind of like the whole idea with the counterexample. I found one x that didn't hold the property that was stated in the universal statement. For the existential statements, there is an x in S such that P of x. Okay, so it's opposite. So let's say I have one thing that has one property. So for example, I have one student in A2 with brown hair. So let's just say that was my statement. I have a student in A2 with brown hair. The negation of that statement would have to be that every student in A2 doesn't have brown hair. That's the only way to show that the original statement was false, was to show that every student didn't have brown hair. Okay, so the next thing we're going to talk about is what are the negations for conditionals, and statements, and or statements. So a conditional looks like this: P implies Q. Its negation is logically equivalent to P and not Q. So, for example, let's use the conditional, if I am elected, then I will lower taxes. The opposite of that statement would be I am elected and taxes are not lowered. So the only way that this would be proven false would be if P happens and Q doesn't happen. The negation of an and statement. For example, my daughter has blonde hair and is 3 years old. So P would be she has blonde hair and she's 3 years old. The opposite of this would be she is not 3 years old, or she does not have blonde hair. So if either one of these is not true, if either one of those original ones is not true, then the statement, the original and statement, is false or opposite. So the negation of an or statement. So let's say that I want cream or sugar in my coffee. The opposite of not wanting cream or sugar in my coffee would be that I don't want cream and I don't want sugar. I wouldn't want either of those things in my coffee. If I don't want cream or sugar, I don't want cream and I don't want sugar.
These last two are our De Morgan's laws. They're logically equivalent statements. We talked about that in class, so it's good to know what those are. Converse, inverse, and contrapositive of a conditional. Which one is logically equivalent to the original? So here's our conditional: P implies Q. The inverse is that you're taking the negation of the antecedent and the consequent. The converse is you're switching the antecedent and the consequent. And the contrapositive is that you're doing both. You're taking the opposite and you're switching the antecedent and the consequent. The one that is logically equivalent is the contrapositive. So, for example, let's use the Ravens as an example. So, if the Ravens win next Sunday, their record will be 2-3. So there's our conditional. If the Ravens win, the record will be 2 wins and 3 losses. Let's negate the consequent. If the Ravens' record is not 2 wins and 3 losses, that means that they did not win this upcoming Sunday. So you can kind of see that they are logically equivalent statements. Let's talk a little bit about the inverse and the converse. Okay, so let's use the following conditional and analyze the inverse. So, if I'm late to work, then I'll be reprimanded. So, let's take the opposite of P. So, if I'm not late to work, then I will not be reprimanded. And let's think about whether or not that's the same thing as the original conditional. Well, in this case it's not, because I could be reprimanded for other things, not just being late for work. And if we look at the converse of that conditional, for example, the converse of the conditional would be if I am reprimanded at my job, then I was late to work. Well, that's not necessarily true. Again, I could be reprimanded for several things, not just being late for work. However, let's look at the contrapositive of this, okay? So, if I'm not reprimanded, then I wasn't late for work. That is a true statement, okay? So, if I'm not reprimanded, then I wasn't late for work. That would be a true statement. Okay, so let's move on to computer networks. And here we have an example of a computer network. And I probably should have just put this on your notes, but it's kind of hard to do this without having an example. So we are trying to figure out how to write this as a logical statement. What's nice is that all of the words are used here, and if you're going to take a programming course, those words probably won't be where the gates are. So let's start with Q, and you can see that the first thing that happens, the first gate I see, is happening to Q, and you can see that Q is being taken to its opposite. So that's where I'm getting the not Q from. And then the next thing that's going to happen is it's going to be combined with P in an AND statement. So I've got not Q and P being combined. And then we have R down here. R is coming up and is being combined with not Q and P in an OR statement. So we have the statement not Q and P or R. And so from here, if I wanted to figure out, for example, what the output of this network would be if P was true, Q was true, and R was false, I could just make one row in a truth table and figure out what the output was. And you guys have had a lot of practice with this, so I don't think this is going to be much or too hard for you. Let's go on to the next problem. Okay, so we're going to talk about the types of valid arguments. The first one is the law of detachment. So remember, these two things that are linked together with the bracket, they are called the premises.
So basically what we're saying here is that P implies Q and P are both true, therefore Q must be true. So if you think about this, if I use just a regular if-then statement, so for example, if it rains, then I will go to the movies. It rained, therefore I went to the movies. Both premises must be true in order for the consequent to be true. Let's look at the law of transitivity. So we have if P then Q, if Q then R, therefore if P then R. Okay, so let's look at the law of transitivity. So we'll go back to our Ravens example. So let's use if the Ravens win, then their record will be 2-3. If their record is 2-3, then they will be one game closer to 500. Therefore, if the Ravens win on Sunday, then they will be one game closer to 500. So this would be a true statement. The last one is the law of indirect reasoning. So our premise is P implies Q and not Q. So those are our two premises in this one. Therefore, not P would be the conclusion. So for example, again, I have this note here, think contrapositive. So if we use that Ravens if-then statement again, if the Ravens win on Sunday, then their record will be 2-3, 2 wins and 3 losses. If their record is not 2-3, the conclusion we can make is they did not win on Sunday. So, and that again would be a true statement, or logically equivalent to the first statement. And I shouldn't say true statement. That's not exactly right. We're just saying that these are valid arguments. So when I say true, I probably should be saying that they are valid arguments. All three of these are valid. Okay, so the types of invalid arguments, we have pretty much talked about the inverse error and the converse error in the earlier slide where we were talking about what an inverse was and what a converse was. The only one that we haven't talked about was improper induction. So here's an example of improper induction. So let's say you have two things, A and B, and both things hold a certain property, and they're both in the same sample space, and they hold a certain property. So you've shown that there is one thing, you've shown that, well, there's two things in S that have the same property. And then the conclusion you're making is that everything in S holds that property. So the way I think of this is like, being stereotypical. So if I say, for example, Paul has brown hair in my class, in my A2 class, and I don't know, and Jeanette has brown hair in my A2 class, then everyone in my A2 class has brown hair. So that would be an example of improper induction. If you think of like just stereotypical comments, people, making racist comments, I mean, that's improper induction. It's invalid reasoning. So, applying a property to an entire group just because you've seen a couple of examples of people in that group having certain properties, you can't apply that property to everyone in that group. So that's one of the things that it's an improper induction. It's an invalid argument, and you can just throw that right back in the face of somebody who's making stereotypical comments. Alright, truth tables. The truth tables for and, or, and implies. So here is the truth table for and. Remember that both P and Q must be true in order for the statement to be true. for P implies Q, remember the only time that is false is if the antecedent is true and the consequent is false. Remember the example we used in class with the politicians who says, if I'm elected, then I will lower taxes. If he's not elected, he didn't lie. So these two down here, he's not elected, he didn't lie, so therefore his conditional, his statement is still true. So don't be tricked up by that. The last one, P or Q. If either P or Q is true, then the statement is true. So the only time that that one is false is if both P or Q is false. Okay, so there's two algebraic properties that you need to know in order to prove that an equation is true. And the two that we're going to talk about are the addition property of equality and the multiplication property of equality. So when you're asked to write your proof, you'll need to know those two. Essentially what we're saying is if you have something that is equal, two things that are equal to each other, then I can add the same thing to both sides of the equation. Same thing with multiplication. If I have two things that are equal to each other, I can multiply both sides of the equation by the same value and the equation will still hold true. The last thing is, how do you show that two statements are logically equivalent? So you basically are comparing the columns in the truth table. So you make a truth table where you have a column for each statement that you're trying to show are logically equivalent. So here I have the statement not P implies Q, and I'm trying to show it's logically equivalent to P and not Q. So I just make a truth table, and then I'm comparing that column with that column, and you can see that they have the same truth values. So therefore they are logically equivalent. Okay guys, that's it.